This is the video podcast for Chapter 17 on distributed hydrological modeling. By now, you should have some exposure to lumped hydrological modeling, and by that I mean models in which we treat the watershed as one single entity, and often we treat the processes that are occurring in the water balance by simplifying them from, say, every individual process to grouping some together and solving for them, in a more simplified fashion. That's what we think of as lumped modeling. And there's an assignment that you're working on right now that is where you're getting experience and understanding in that form of modeling. But at some point, you'll see that there are a lot of limitations to that. It's not representing all of the processes that we know exist. It doesn't have a strong stochastic component, if that's important for something that you're looking at. Those models are designed to tell us about the stream flow out, but they don't necessarily tell us accurate representations of the storage and fluxes of other components. What does it mean to say like a curve number? What is a curve number? In reality, it's not something you can go see, right? I can go see a color, but I can't go see a curve number. So are there parameters that we could derive that are more realistic and understandable to the physics of the problem? Also, we have this just tremendous development of technology related to remote sensing, whether it's airborne or satellite-based, all kinds of new data collection, and then geographic information systems, what we call environmental informatics, which are databases and other kinds of procedures and techniques for coping with large data sets. And then we have vastly superior computer technologies to solve more complicated problems than we could before. Lastly, we might really matter to us to understand the spatial patterns of the water balance that exist inside the watershed and not just see the overall fluxes. So that's where distributed hydrological modeling comes into play. Here we have models that are going to discretize the landscape in some fashion or another. This slide shows one example of that where we're using what I called previously a voxel-based approach. So a voxel is a volume pixel. A pixel is usually like a square representation of the surface, but when you add a third dimension, it creates a volume. So we can call that a voxel. And so we by discretizing the landscape, then we can make this down to a scale where the processes in an individual voxel are actually honoring the as we are understanding the equations and representation at that pixel scale. So if you make a pixel that's like a 10 meter by 10 meter by 10 meter cube, then if we talk about infiltration, you could go out and measure something at that scale and use the equations and parameters that you measure in the field to parameterize that model. The first thing in order to do distributed hydrological modeling is you have to have a digital representation of the land surface. That can be called a digital elevation map or model or a digital terrain model. So you've probably heard the term topographic map. That would be if you actually have a piece of paper that's a map, or a map is something that you would print out. But in terms of the data itself that represents that landscape, then we can just talk about the digital terrain model. It's like the set of numbers or equations that represent the surface. And there's generally three different ways to go about that. But traditionally, like if you think about it, how we got to these in the first place, the United States government and many governments around the world paid geologists and cartographers and surveyors to go out and map the landscape, usually yielding a contour map. And so on the left here is just like a black and white rendition of a contour map. Here, each line represents locations that have equal elevation. And as you go, your elevation's either going up or down. In this particular image, you don't know which way is up or down. Nothing in the image tells you that. But usually you have numbers or some other indication to provide that sense of height. If you then go in, take this map and you scan it, then you can put a dot and digitize all along these contour lines. And that's what the second map shows. You see all these little tiny dots along the contour lines. And then from those dots, then you can interpolate, which interpolate means to calculate values away from those points of observation and create a grid. And so A grid is a basic representation of the land surface where at each point or node in the grid, you have an elevation. So at each of those points, you have an X and a Y and a Z. So this is the simplest way, what we could call a grid model, which is also called a raster. And so here, the X and Y directions could just be given numerically in terms of column and row number, and then the value that's inside, that's stored there, is the elevation. So this would be a matrix representation where you don't have to explicitly write down the X and Y coordinates. You just have a matrix of numbers, and the location in the matrix is the X and Y position. On the other hand, you could actually have a text file that has like X coordinate, Y coordinate, and Z coordinate. So that would be another way to go. And on the right is a height map, just in a grayscale from, again, you don't know necessarily which is the highest or lowest, but usually black might be taken as the lowest and white taken as the highest. These days, we tend to see these digital terrain models with resolutions of 30 meters by 30 meters or 10 meters by 10 meters. It's also important to note that because of that resolution, unless a channel is bigger than 30 meters and unless there was a mapping effort to go and get the elevation under the water, then a digital terrain model of a watershed is usually not going to actually include channels and the attributes of channels. Another way of representing the surface that's actually much more efficient is called a triangulated irregular network, or TIN. In this case, the data don't have to be gridded with equal intervals. Instead, they can be irregularly spaced, as you see here. And then what you do is you fit a triangle to any 3 points, and the whole surface gets this kind of triangulated mesh. And using the equations for that triangle, you could then interpolate points for anywhere else on the surface. A tin is a more efficient representation because in areas that are flat, there's no reason to have a lot of data. So you can see in the lower left here, these areas with really large triangles, they don't have large slopes or significant landform change. So why waste space and computation time putting a lot of grid points there? On the other hand, where the landscape is changing a lot, then you would want to put a lot more grid points. Whether you have a raster or a tin, there's a lot of really important topographic attributes that you can compute using this kind of data. And this is a table that lists several of those attributes. For example, you can get, just the basic elevation, obviously. You can compute slopes. You can get to contributing area, local slope, overall slope, relief. You can even get the curvature of the landscape. Is it convex? Is it concave? So there's all kinds of things. And really, I could give you an entire course on ways that you could use that information. In fact, I do teach such a course in hill slope geomorphology and sediment budgets at the graduate level. To give you a little bit of a flavor of how some of the significance here, it's really, really important to eco-hydrology whether you're in a part of the landscape that's laterally converging or diverging. And I know this is not in English, but you can see that if you go along the ridge top here, we have this very long length. And all of that area is contributing to this one point. So essentially, this is delineating the watershed to that point. On the other hand, if you look at the white area down here, you can see that from this one point, water can diverge away. So that actually, instead of having a watershed outlet as one point, you have all of this low-lying area is being fed by this one point. So whether the landscape is concave or convex has a significant role in determining how water flows and how moist the soil is throughout the landscape. It's also possible that you have even side slopes where water just has a one-to-one relationship from upslope to downslope. So all the water from a point just goes straight down and ends at a point. The reason why this is important for hydrology is that a lot of distributed models take advantage of something called a topographically derived wetness index. And this is going to relate to something that I talked about in a previous video podcast that was called the variable source area concept. You might remember from that concept that I mentioned that it tends to be wetter when you're close to a channel and then drier when you're away from it. So if you're up at the very top of a watershed, water that falls on that tends to not stay there, drains away. If you're in a hollow, that's a low-lying area that lots of land is converging to, you may not have overland flow yet, but you might be quite saturated. That concept can be turned into a quantitative equation, which is the one that's shown here, and we call it the topographically derived wetness index. It's like all other things being equal in terms of soil types and vegetation and everything else, just depending on what the topography is, we can expect some areas to be wetter and some drier. The equation is the natural log of the ratio of contributing area to a point and the slope at that point. So the contributing area is all of the land that's draining to that point, and the slope is not the slope of all of the contributing area, it's the slope at the point that you're interested in. Slope can be given in either degrees, which is what beta is here, B is slope in degrees. That then gets converted into a number using tan beta. And then the contributing area, so if we take a slope and we convert it to tan B, then we can see that for any given contributing area, we can get a wide range of wetness index values. So the steeper it is, there's an inverse relationship here, and you get a low index for a steep slope. It also should make conceptual sense that the more contributing area you have, then the more water you're going to get. This is a map that helps to illustrate the topographic wetness index in relation to the contours of the topography of the land. So the places that are shown here with closed contours are high elevation areas, and then places where, like over in the right here, would be the lowest elevations areas. And I'm just interpreting that from the combination of the colors that represent wetness and the contour lines. A closed contour is a hilltop, and then the water is draining away from those hilltops. So the colors then represent the topographic wetness index, with a low value being dry and a high value, like kind of dark blue to black, being very, very wet. So at the top of a hill or along the crest or a nose, and a nose would be a place like this. Here would be a nose. Here's another nose. Those are areas that tend to be dry because they have a small contributing area and a high slope. On the other hand, in the channel network itself, or even if there's no channel, just because where flow is converging, it's going to tend to be wetter. Let's see, is this okay? So if we start with a digital terrain model from low elevation to high elevation, we can figure out what is the contributing area for each point or grid cell in the raster. We can also extract the slope, and then you put those two together to get your topographically derived wetness index. And so here you can see that the areas that have high catchment area are going to really pop out as having a strong amount of moisture. Here, blue means a lot of moisture, red means a soil moisture deficit. The slope pattern is a lot weaker in its influence, but you can see it very strongly in this section here that's on the hilltop. So now we know what areas are wet and what areas are dry. And remember, we don't know if there's a channel necessarily, we just know they're wetter or drier. Now let's say that we had enough moisture to actually have overland flow. How do we create a flow path? Okay, so the way we're going to figure out the flow path, like how water actually makes its way down the hill, is to use something called a flow direction algorithm. And I'm going to show you a representation here that's a grid-based approach, because that's the simplest thing to understand. Now if you think about it, if you have a hill and you could just pour water on the hill, obviously it's going to flow from high areas to low areas. But if you break it down in its detail, which way is the water exactly going to go? We know it's going to go downhill. Will it go equally in all directions that are downhill? Will it go in multiple directions? Will it all go in the path of steepest descent, it actually isn't something that is necessarily obvious. And yet, in terms of hydrology, if you have a distributed model and you're moving water from cell to cell, it's essential to get this right. But in fact, there is no real agreement about what is right at this point. So I'm going to show you a couple of different approaches that people have invented to deal with this. Imagine that we have 9 cells adjacent to each other as shown here, and we're interested in where the water from cell X is going to go. The numbers that are shown in each square are the elevation. So 1 would be the lowest elevation. Well, no, I take that back. These are just numbering. 1, 2, 3, 4, 5, 6, 7, 8. So this is just numbering. So the water could go in all directions, which would be illustrated here. Now, let's look at if we actually have the elevations, which is where I thought I was looking at, which is over here. So compared to the elevation that we're in at 18, the water is certainly not going to flow uphill. Now, it might splash a little bit uphill, but in terms of flow, if these are 10 meter by 10 meter or 30 meter by 30 meter cells, it's not going to go from an elevation of 18 to 21, 25, or 26. So we could eliminate those very easily. But what about the rest of these, 14, 16, and 11? So those cells could all receive the water. So we need some approach to distribute it in those downhill directions. The simplest approach is to send all water on a path of steepest descent. This is called a D8 approach, or single flow direction. So here's another elevation matrix. So starting from 78, the lowest cell is 67. So you can see the arrow is pointed in that one direction. And so for each cell, that's the assessment, like 74 to 53, it's pointed that way. From 69 to 53, so it's pointed straight to the right. So each one of these arrows is pointed in the path of maximum descent. Notice that it does permit diagonal flow, so it doesn't have to be just down or across. It can be in the diagonal. And then we can draw a flow network that is lines that shows the connectivity between those cells. If we go through the effort then of taking the contributing area and passing the water down, you can then figure out what's the total number of cells and then area that is contributing water to each cell. So here with the D8 approach, you can see that there is a very clearly defined area, a very high contributing area, and that will be the channel most likely, if there's enough area to produce flow. But notice that there's a lot of very linear features here, like these streaks that are across. They don't seem very realistic, but that is what you get with this approach. So the nice thing about this D8 method is it's very fast and efficient. It's built right into ArcGIS and other tools, and it's really good if you have pretty simple structures like straight side slopes, simple systems. If you have very flat terrain, it's horrible. If you have ridges that are highly curved, then that curvature can create problems. Another approach, which is called row 8 SFD here, is one in which you have a blend. So you consider the fact that you want water to go downhill, but you're also going to be distributing it in proportion to the slope and also adding a random component. So let's look at all the neighbors with low elevation and calculate the slope. And then we're going to weight the probability that water is flowing from one cell to the next on how steep it is. So the path of steepest descent has the most likely chance of receiving the water, but then you have to draw random numbers and see where it goes. And so that adds a stochastic element, which is very realistic, but it isn't necessarily repeatable. So if 10 different people make a model using this algorithm of the same landscape, they might get 10 different answers for what the hydrology is going to be. Then this, like MFD means multiflow direction. So this is a case where we're going to eliminate that random component and just distribute it directly in proportion to the area. So in this case on the left, about 66% of the water is going to go down this way, 23% diagonal, and 15% this way. And then these are just 3 different scenarios. So it's just like a multi-flow direction. We're going to allow water to go in several directions, all downhill. And the steeper a direction is, the more it's going to get. The next one is where we're going to, oh, no, okay, so that is, all right, so this is now a visualization, sorry, of that approach. And you can see that it has significantly smoothed out the effect. Let's see, did we, yeah, okay. So, right, so here was the D8. Then the row 8, it still has, still fairly discretized. It has more winners and losers, it looks like. And then you come down to here, and it's highly smoothed out because now we have water that's spreading out in more directions. So now we have a way of having water flow downhill, and we've got these 4 different algorithms, and really there's a lot of algorithms that make these different trade-offs between multiple flow directions and path of steepest descent. And now we have to decide just how much contributing area do you have to have for a channel to be there. So a channel is formed when you have enough flow to erode the bed and create that geometric shape. The simplest way to do this is to say that when you have a certain amount of contributing area, then you're likely to have enough water to cut a channel. Of course, that's going to hinge on the precipitation rate. So a very low precipitation rate might not even have a channel with a very high contributing area. So there's more physics, in fact, involved, but the simplest first step is to just do it this way. And so in this case, we could say the same watershed, and we could say, well, let's assign a very low contributing area to call it a channel. Then the channel network is going to be highly articulated. One thing we could do is we could use what's called the USGS blue lines. So if you look at a United States Geological Survey topographic map, you'll see that the map includes blue lines that represent the presence of, like perennially wetted channels. Now, usually there are geometric channels that are further than that, and remember from the variable source area concept, the occurrence of overland flow, which may also include channelized overland flow, it varies, so it isn't necessarily just fixed. But you can certainly look at the blue lines and say, well, among that, this highest contributing area approach is the closest. It's not perfect, but it's the closest. So some places it's got more channels that probably shouldn't be there, and in other places it's not going as far as it should. So we use this term truncation level to represent the contributing area number, that if you have more contributing area than that, you are in a channel, and if you have less, then you're not. One of the problems with taking a 30 meter, 100 meter, or even a 10 meter DM and creating channels in this fashion and flow directions is that what happens when you have a big flat meadow, like an organic soil flat or mineral soil flat. In this case, here's a map of Mars, I believe, and if you take a DEM of a very flat surface, you're going to find that there's a lot of noise, and of course you're forcing there to be flow directions that aren't really natural. And so typically then there are a lot of problems like this, and there are standard procedures that are beyond the scope of this class, but there is software called ArcHydro that can be gotten for free along with ArcGIS. That's one of the tools that you can use to fix a lot of these problems. Okay, so here's some example maps that show what you can get out of a distributed hydrological model. A is a digital elevation model. B, this shows the direction that water is flowing, and here's the scale, well, that goes for that. C is the slope in degrees. Then D is the aspect, so like, is it facing north-south? This is the topographic direction that the land is pointing, whereas B is which direction is the water flowing. Then E is the log of the contributing area, and then F tells us essentially it's a metric for how many channels are connected together. I'm not giving a very good definition because I kind of don't really want to go into it, but something called Strahler stream order. It's like where multiple streams come together, then you can form a higher order stream, and I really kind of don't even want to go there. Okay. So now let's take a step back because we've been really far in the weeds. We've addressed the getting a digital terrain model, taking the digital terrain model and determining where it's wet and where it's dry, If you were to have overland flow, determining what direction that flow would go for every cell, and then finally, whether you have enough contributing area to generate a channel or not. And that's the simplest approach for that. We're not going to get into details beyond that. So at that point, we're ready to kind of dig into the meat of the distributed hydrological model. The way this is going to work, in the upper left, we have all kinds of data. And now it's not like we just need one curve number or something for the whole watershed. We're going to have spatially distributed data for every kind of point. We could always assign something as a constant, but we have the opportunity to get that. So we're going to have inputs. So that means like rainfall. Well, that's the main input, but you might also have stream flow or groundwater flow, I guess. So that you're going to have a spatially distributed map of that. And of course, we often don't. We often have like 1, 2, or 3 gauges if we're lucky. So you have to have a way of taking the data from that gauge and distributing it across the landscape. In addition to those inputs, you're going to have geographic data, topography, soils, land use, vegetation. Here are the examples there. And then you're going to have to put those together with equations in the model to then get your spatially distributed water balance, component, storage volumes, and fluxes. Okay, so another thing is that when you have a landscape, and here's a picture of a watershed, then you still have to go out and make field measurements, and then if you're making those field measurements, you need some way to aggregate that information up to get to an individual pixel. So we could take this landscape and grid it, and then within an individual cell, you might have a variety of patterns that are taking place that you then have to get that average value for. And then we could also look at the frequency distribution of that property. And in the absence of information, some people will take that distribution, like maybe you sample the watershed and then use the distribution to stochastically assign the values for geographic inputs or model parameters. So let's say, for example, for a model parameter, you have something like hydraulic conductivity of the soil or permeability of the soil. You might go out and measure that with a statistical sampling campaign, get the distribution, and then randomly assign values to all the rest of the cells. Okay, now here's a very important concept that is going to be a little bit difficult to understand. So we have these 3 different kinds of things. I'll go back in here. You've got input, by which you mean like precipitation. You've got geographic data that is also going to be input into the model, but it's not like the driver of the hydrology the way rain is. And then there also are what we call parameters. So parameters are, like variables or constants that are in the equations that relate one thing to another and, sometime get in there. You might remember from the Penman-Monteith equation, we had things like canopy resistance or aerodynamic resistance. Those were parameters that you had to figure out through field studies, and I showed you a lot of examples of that. So now, let's say you have an input, and let's say rainfall. Well, one of the interesting questions is, what is the effect of that on the output value? So the x would be some kind of input value or parameter, and y would be the output. And so what the model might do is the model might take a number, and it's going to give you, let's say you had 4.5 inches of rain, and then as a result of that, you had 38 CFS of outflow. Well, on a marginal basis, as you go from 4 to 4.5 or 4.5 to 5, do you find that the numbers in the output are disproportionately larger? So in this case, you can see that like 4 goes to say 25 and 5 goes to 55. So that's a huge spread. That's a very strong amplifying effect. But let's say you're in a case where you go from 7 inches of rain to 8 inches of rain, but you only go from a runoff of 89 to 94, right? So that's a highly muted effect. And the reason why I'm bringing this up is because with a distributed model, well, this was true even in this SCS rainfall runoff curve number approach that I showed you. I showed you a map that had rainfall on the x-axis, runoff on the y-axis, and then these diagonal lines with curve number. And it was largely a linear response you'd have to go back and see if there was an amplification in the numbers. But with a distributed model, the equations are far more complex. And as a result of that, it's not obvious. Like, you can't just look at that and necessarily say what the effect is. Some people can, but depending on the model and its level of detail, that may not be possible. So we can then use the model and experiment to see what that is. And that's a process called sensitivity analysis. So you build the model, and then you want to know, well, I have something like rainfall input. If I were to change the rainfall, do I get a disproportionately larger response or not? And the reason why this matters is because, of course, any number that we put in is usually not certain. The numbers we put in are uncertain because we've measured them in the field, or we got them from a radar or something like that. And so because of that, there is a chance of error. And we're very concerned in science about how does error propagate through and disturb the results that we get. So here's an example from a distributed model in which they did a sensitivity analysis on the error in rainfall for 5 different watersheds. And what you can see is, like, if you had no error in rainfall, then of course you get a value for mean annual runoff, okay? And the y-axis is going to show us for any given amount of error in rainfall, what is the error in mean annual runoff that occurs with this particular model. So for example, as you add, say, 4% error, like you have too much rainfall in the model, then you end up with some amplification because you go from like 4% input to, like about 10% runoff. So changing inputs up and down in 2% intervals and then check the response. You can see it's a linear response, but it is amplified. So if I have 8% too little rainfall to 8% too high, we're going from numbers of about 20 to 30 in the negative direction to numbers of about 20 to 30 in the positive direction. So it's a percent difference of 40 to 60%. So that it should be no surprise, really, that if the rainfall input is wrong, then the model output is going to be wrong. Now, let's say we have another variable such as potential evaporation. In this case, if we go from -8 to +8, we go from about a 1-to-1 relationship. So a -8% error has anywhere from a muted 5% to about 1-to-1 8%. And then you come over here at the positive 8% range, we're at like a -3.5 to -7. So the total difference across this range is something like an error of 16% in potential evaporation gives you an error of like 8 to 12%. So clearly, rainfall error in this model has a much stronger amplified effect than error in potential evaporation. As a result, as a practicing hydrologist, where would you put all your money in measuring right? Precipitation or potential evaporation? And the answer is that if you're using this model, you better put it into getting your precipitation as accurately as you can. So all of these models have what I've been calling parameters, and here's a list of parameters from one particular model. It's not so important what the acronyms are. I will never ask you this, but I want you to get the idea that models have parameters like interception storage capacity. Now that's a parameter you know pretty well. But then, exponent used in relationship between infiltration sorptivity and soil moisture status. Okay, so you can read those on your own. And then what this shows is if you introduce error of 10% in a parameter, what is the error in runoff? If it's a linear response, then you would have 10%. If it's less than that, it's a muted effect. And if it's more than that, it's an amplified effect. And here's these different coefficients. You can see that SQ, which I told you before, that actually yields the greatest error, and it disproportionately affects Stewart's Creek number 4, whereas other ones, it doesn't. So that's also pretty confounding. Like, not only do we have to worry about all these things having errors and sensitivity, but it's not the same for every watershed, which means that you have to do a sensitivity analysis every single time you make a model. I would like to bring this back to one of the themes of the class, because the theme of the class, one of them that we have, is the effect of humans. And we had a whole video podcast that dealt with deforestation effects. And last time, in talking about lump modeling, I also came back and gave you a bonus question to try to calculate, using the curve number approach, what would be the effect of a change in land use on runoff. Well, another way to formulate the question was done in the same study by asking how much logging would it take if we did it in the model to get a runoff response given the fact that the model has uncertainty. And so, this is really important because remember in the field studies, any study, like very few studies even bother to look for runoff effects if you log less than 20% of the watershed. Of course, a lot of studies just do 100% logging. But it would be really helpful to know just how sensitive watersheds are to something like logging. And so in this case, there's 3 sets of answers here. Like for the 4 different watersheds, if you have pan coefficient errors, then you need to log in the model 7 to 16% of the land before you're going to see a runoff response. If there are model parameter errors, it's very wide. I mean, 6%, so that's nothing. But for Blue Jacket, given model parameters, you're not going to see any effect of logging on streamflow response in the modeled watershed until you've logged 65% of the area. And then rainfall falls in between, so anywhere from 12 to 43%. So it's really important, this whole idea. So you should spend some time thinking about this, that whatever information you put into a model has error. The error is going to have an effect. And the effect could be muted by the model or it could be amplified by it. That all depends on the structure of the model. Usually when you first are new to a model, you don't know. And you can see that it varies a lot by watershed. And so as a result, you really have to spend some time doing this thing of a sensitivity analysis, systematically varying each input to see how the system of equations responds in that case. And then if you have a question like logging, then you want to know, well, I may not even know how much error I have, but I can see that I better do a substantial amount of logging if I want to see that effect in the model. And that's the same thing in the field studies, that you have to clear cut quite a bit before you see a runoff response. Okay, so now I want to switch gears. I've introduced you to the idea of a distributed hydrological model without going into the nuts and the bolts of it. We're going to get into that more in future lectures, so that's not going to be what I want to focus on now. But let's assume that you have a distributed hydrological model, you've built it, you've run it. How do you decide if it's good? Well, the first thing you can do is use the time-honored method we've used in all modeling. Compare a predicted versus observed hydrograph. Here's the observed wiggles going up and down, and here's the predicted. And are they doing the same thing, or are those totally not working together? Another thing you can do would be to look at lumped values, like is the total amount of water in a year that you predict the same as the total that is observed. So that's the easier standard. Remember from the first assignment, you had to do that comparison for gaseous model. And so in that case, error in totals is generally easier than other kinds of errors to achieve. Another thing you can do is qualitative assessment, like are all the streams that are actually flowing in reality producing runoff in the model? If they're not flowing in the model, then you've got a problem. Does the model show an expansion of runoff producing areas during wet periods? So in other words, is the variable source area concept functional? Upslope areas of hill slopes, they shouldn't produce runoff except in the highest rainfall areas. So again, that's that variable source area idea again. And then the other thing is that these models are producing water tables. So the water table better be pretty close to the ground surface or at the ground surface where you have a channel. And then of course the last thing is you sure get some pretty maps in GIS. So if you visually compare 2 maps, do you see that they look similar? Okay, well, let me illustrate these concepts with a different distributed hydrological model. In this case, we're going to ask the question whether the model is more sensitive to getting the rainfall map correct or to having the vegetation map correct? So this is a very relevant question for ecohydrology. Should I put more time into getting my land cover and land use right or my rainfall input? The experimental design is I'm going to have simple or complex maps for distributed rainfall. That's A or B. And then I'm going to have simple or complex methods to distribute leaf area index. And in these distributed hydrological models, LAI is the primary representation of vegetation. Then I'm going to run simulations with all combinations, like AC, AD, BC, and BD. And then relative to the combination that has complex rainfall and simple LAI, I want to see whether the other combinations are performing better or worse. This is a map, and I know it's hard to see just in black and white, this kind of grayscale, but here we have a distribution of rainfall. So white means low rainfall and black means relatively high rainfall. And you can see that the simple representation, is called a 1D interpolation. It means that the amount of rainfall increases as elevation increases. B is a 3D representation, so depending on the latitude, the longitude, and elevation, then it decides how much precipitation there is. And you can see there's a significant effect, because on the left you basically just see the DEM. I mean, you can see the channel network, the valleys are so far in there. Whereas over here, the representation is less guided by that, and you can see a very strong positional effect down in the southern end. So that's a really meaningful difference. Here's a comparison of the leaf area index map, and it's really hard to see. I apologize for that, but this is from 1998, and there wasn't a lot of color maps published at that time. So here we have a leaf area index going from 1 to 6, and in the first case here, A, we're assigning leaf area index to each forest cover type based on a forest map. And then B over here, and I don't know, well, okay, right, so this A and B, that's just for the figures, but I'm saying C and D because I'm referring back to my experimental design. So that's what that is. So this case here with C was based on a map, and D is based on a satellite image. So using a satellite image, you could estimate the leaf area index, and you can see it's a much more complicated spatial pattern. So we have simple and complex rainfall, simple and complex leaf area index. So what matters? Okay, so this shows 3 hydrographs. On the x-axis is time, the y-axis is an amount of flow. This is for the BC scenario, so that's the scenario with complex rainfall, simple leaf area index. And then there's 2 lines. The solid line is the observed flow, and the dashed line is the predicted flow. And this is where just visually you can look and say, do the wiggles look like they're matching? And of course what we always see is models do pretty well, except when there's water. So every time that there's a big spike, well, here's a rainfall event, and the model way over predicts all of these events. It seems to be like an over predictive model. When the flows are sort of medium, the model does well, but here's a case where there's some significant difference. So it's one of those funny things, like hydrological models perform well when it's not raining. Well, doesn't that defeat the point of hydrological modeling? But anyway, I digress. So if we look here, the mean is an observed test, 1.7 millimeters per day of runoff, and predicted was 1.62. So, of course, you take all that variance and you summarize it down to a mean value, it makes the model look pretty good. So now let's go to a more complicated situation where we distribute the leaf area index by the satellite map. And you can see that there's no improvement whatsoever in the predictability of the mean condition, and there's some change in the wiggles, but not very much. It basically means that this model is not sensitive to leaf area index, converting from this, this C to D approach. On the other hand, if we take the 3-dimensional precipitation distribution and simplified it to a 1D interpolation, we do get a significant effect. So whereas the observed mean flow is 1.7 millimeters per day, that drops to 1.19, and that's a significant degradation in the model. If we look at the map, so these are shown in color, White is no runoff. Black is full runoff, or not full, but the highest here. Then the BC scenario is shown here. You can see there's a lot of flow in the southwest. If we go to the simplified scenario, that turns off. And then if we spatially distribute, you do see a little bit of a stronger effect there. But, it's like, how do you quantify these map differences in a quantitative way to really assess that? And I have answers to those questions, but it's definitely beyond the scope of this class. Okay, so that's the end of the presentation. We haven't gone into like how do you actually make a distributed hydrological model and what are the hydrological fluxes in great detail. Obviously, there's going to be a lot of similarity with the equations from the lump model, and we will be looking at those case studies in subsequent video podcasts. The main point here is you need a digital terrain model. You need to determine flow directions. You need to determine where there's channels. And then you have to account for the uncertainty in all of the inputs to try to see how sensitive the model will be. And finally, you have to validate to say, is this model good, and not just at producing stream flow at the outlet, but actually in producing all the spatial patterns and magnitudes and fluxes of water.